want to finish off a couple more of those limits on sequences, because there's basic techniques that use a lot, and then there's just ones that you have to, special cases, or you have to work at them to get the answer. I've covered this version before, but I want to kind of start at this one, because this is just, you do it because I tell you it's true. And this is a version of question 33. And we're going to be finding the limit of a sequence, and it's 1 plus 2 over n to the power of n. Now, can you remember what I said yesterday? It was just, trust me, I'm a mathematician. Can't we just write down the answer to that? There wouldn't be any proof that I would expect from you, just the knowledge that you know what it's equal to. What is that equal to, that limit?
E to the n.
Not quite, but you're darn close.
E squared.
Yeah.
Sorry.
No, E squared. Right. I'll write down the general version of this. The limit, as n tends to infinity, of any fraction that has a 1 plus a fraction over n, right, 4 over n in this case, to the power of, say, 3 over n, is a power of e, and it's whatever 4 and 3 is. So in this case, it would be 12. And I promised you a general one, so let's do that one. That's it. You just, you know, it is what it is. That's what it's equal to. You accept it for the time being. Okay. I believe, didn't we do the 1 plus 1 over n to the power of n and show you it was darn close to e, which is what it should have been, right? E to the 1. Remember, we did it in the calculator. It's not a proof, but it kind of gives you an idea that it works. Yeah. How about this one? This is a version of question 34. Because I talked over a couple of these, I don't think that's as good as seeing it. As it stands, brute force will not work on this, because you get the log of infinity, take away the log of infinity, and infinity take away infinity isn't 0. Could be anything. Okay, so any suggestions for what my next line of working should look like? What do I change this subtraction of 2 logs into?
Can't we combine the 2 logarithms into one single log?
And it's first log subtract second log becomes a division. Can you remember that from the rules of logs? And then I'm going to do a switcheroo. Hey, that rhymes. Hey, I'm going to do a switcheroo. I should do that again sometime. You are allowed to do this switcheroo thing. If this was e to the power of that, sine of that, square root of that, I can't think of any others, but you know, secant squared of that, can't you just bring out the operation, in this case the logarithmic function, and just find the limit of what's inside? And there's a nice piece of math that says you're allowed to do that. Okay, what's this guy in the middle going to be? What is his eventual answer going to be?
3.
Yeah. So won't the answer be the natural log of 3? How could you prove that that was 3? There are 2 methods you could use.
The division by n squared, or you could use L'Hopital's rule.
Right. And although I haven't written it down here, I would expect you to write that down in a test question. Now, what would I expect you to do in WebAssign? Well, WebAssign's not very good. It just has a box where you put the answer. So you won't actually show any working in WebAssign. But remember, I keep pushing this, and unfortunately, it doesn't seem to matter how many times I push it. Some of you are not going to pay attention, and come the test, you're just going to stick in log 3 and think you're good. And so I will do what they say way back when I started teaching. If you want to get a point across, you should always say it 3 times. So here goes. If you only give me the answer, I'm not going to give you any points. If you only give me the answer, I am not going to give you any points. One more time. If you only give me the answer, I am not going to give you any points. So nobody in this class is going to complain after test 1, but I got the right answer, you didn't give me any points. Because I am going to say to them, if you don't give me an answer, I'm not going to give you any points, right? So you've been warned.
On the first problem of 33, is that e to the 2n or is it just e to the second? I can't tell if that's an n or a scribble.
It was a scribble because someone started with an n and then we fixed it. So it's e squared, there's
Okay.
no n. There are a couple more to go. These are ones we haven't tackled, although you may have seen factorial before. And this is also going to be one of those exceptions to my rule that I just nattered on about. Some questions you can only put the answer. So for instance, see this question up here? If I gave you this in the test, all I would see is e squared, then you're totally fine, right? Or e to the 12, depending on the question. The answer to this is infinity. In fact, the answer to this is divergent.
What is that first one called? Number 33, the general rule. There was a name for that, like.
If there was a name for it, I'm not sure what it'd be, but I just call it it'd be an exponential rule, I guess. It's a property of limits that limits of this particular shape end up being powers of e. Now, and this one, technically it's infinity, but that's what you write down. And how do I know that? Well, I'm going to give you another piece of knowledge that we just accept. Do you recognize n factorial? You know, it means 1 times 2 times 3. So can you imagine what infinity factorial looks like? Well, not very easily, but wouldn't it go 1 times 2 times 3 times 4, and then you just keep going forever? There is a hierarchy of size, an order of size. What I mean by that is that if you make n go infinite, some things are more infinite than others. Side issue, and then I'll talk about this. Infinity is a weird thing. We use it in some ways as if it was a number, like it was 42. You know, when I do brute force and I'm plugging in infinity in like it was a number, and I'm doing some weird calculations, like infinity squared still infinity, you know, things like that. Infinity plus 4 is still infinity, right? We do some calculations. It feels a little bit like I'm using it like a number, but it's more than that. There is different types of infinity. So here's an analogy to try and get that idea across. Would you agree that there is an infinite number of whole numbers, right? 1, 2, 3, 4, 5. Forever, right? There's an infinite number of whole numbers. Would you agree that between 0 and 1, there's an infinite number of fractions? There's a half, a third, a quarter, a fifth, a sixth. Isn't there between 1 and 2 an infinite number of fractions? 1 1/2, 1 1/3, 1 1/4, forever, right? So if I went and said to you, there's an infinite number of fractions and there's an infinite number of whole numbers, would you also accept that the infinite number of fractions is more than the infinite number of whole numbers? In other words, there's more fractions in the universe than there are whole numbers. Now, they're both infinite, but can you see one has a bigger version of the other guy? Does that make sense to you? That infinity can have degrees of infinitiness, right? You can be an infinite and then you can be a really infinite. Okay, that kind of thing. So order of size says this. If you take powers of n, like n squared or n cubed or any power of n, that's pretty low on the infinity scale. So if you make n infinite, infinity squared is infinite, but it's pretty low, right? If you do 2 to the power of n, it's bigger than n squared. Pick a number like 10. Isn't 10 squared 100? But 2 to the power of 10 is 1024. You can see it's already bigger. Going this way, the log of n, right? The log of infinity is infinity, but it's a very weak infinity. N to n factorial is a really big infinity. You know, when n is infinity, infinity factorial is, well, technically, aren't the last two numbers infinity minus 1 times infinity? Can you imagine how big those two guys are? And that's without all the other ones that came before it, right? There is one more guy that I want to put here that's even bigger than n to the factorial. Can anybody think of who takes the biscuit? Who is the biggest version of infinity that you're likely to meet in this list?
N to the n?
Yes. Would you agree infinity to the power of infinity is scarily big? Isn't it bigger than infinity squared? Now, why is that order of size important? If you ever get a limit that's a fraction, and the term on the top and the term on the bottom are from this list, you can find out what the answer is going to be to the fraction. Unfortunately, or fortunately, I guess is a better word, there's only two answers. It's going to be 0 or it's going to be infinity. And it depends on a little battle. Would you agree that 3n factorial is going to murder 2 to the power of n? And so the guy that's the biggest is on the top, makes the answer infinite. If I give you this fella, wouldn't n to the n murder that fraction? And so in that situation, do you see the answer is 0? So figure out who's the winner, who's the biggest. If he's on the top, the answer is infinite. And if he's on the bottom, the answer is 0. Does that make sense? If we assume that we know this order correctly, which we do, would that seem reasonable? So you're not going to get the answer 5 or 7 out of these kind of questions. You're just going to be, it's going to go to 0, or it's going to go infinite. It's going to diverge on you. So how about this fella? Okay, I know that guy says -2, but he's really just the same as 2 to the end, doesn't it? I mean, it alternates, which is a bit of a nuisance, but it isn't really a big deal. Who's going to win? The power or the factorial?
The factorial.
And it's on the bottom, so what's the answer?
0.
Do you think it matters if the answer goes +0, -0, +0, -0? No.
No.
And if you did that as a graph, you'd probably find out it would go something like this. See how it would alternate but get closer and closer to 0 as n got bigger. So this one is the final one, and I'm warning you right out the bat. Danger, Will Robinson. If you don't know the reference. And I've warned you, trick question, be careful. What is the answer to that limit?
Infinite.
Does not exist.
Does not exist, and we will call it divergent. Now, you might be looking at that and thinking, wait a minute, forget about this for a minute. What's the limit of n over n plus 7? Well, the answer is 1, isn't it? But what happens with this guy? If I sketched it and I put, say, 1 here and -1 here, what you would probably see is that it would look something like this. Put it as a low dotted lines. Can you see that it would get closer and closer to 2 different numbers? It would get really close to +1, but the next number would be even closer to -1, and the next one would be even closer to +1. A limit is not allowed to be infinite. That's why we call it divergent. It's not allowed to does not exist, so we call it divergent. And it's not allowed to be 2 different numbers, 1 and -1 in this case. So we call that divergent. See how divergent's a nice phrase because it just catches all the other situations, so we don't need to be too specific about what the problem is, just that there's a problem. Now, that's us finished with sequences. So let's start with series. I believe there's 11 sections in chapter 11. One of them deals with sequences, and everybody else, in one way or another, deals with series. So you can imagine that series are much more important. There's a lot more to them. And so we need to understand what a series is. And what we're going to learn over the next few weeks is to find out whether a series converges or not, which basically means, does it have an answer, a numerical answer or not? And in some situations, we're also going to try and find out what that answer should be. So let's begin right at the beginning with what a series is. Well, a series is the sum of all, that's important, all the terms in a sequence. So imagine I have a sequence and it's 1, it's a half, it's a quarter, it's an 1/8, it's a 16th, right? And that sequence would be called 1 over n. Are you happy with that sequence? In fact, doesn't that sequence have a limit of 0? 1 over n becomes 0, right? So what would the series look like? A series is what you get when you add up all the terms of a sequence. So in this case, the series would be a single thing. Because you know, if you add all these up, you would hope at least, that there is a single answer. So a sequence has lots of terms to it. A series, technically, if you calculate it all the way to the end, will have one of 2 answers. It will either be equal to something, in this case, it's 2, or it will diverge, mostly because it's infinite, but it doesn't need to be. So diverge just means that when you add up everybody in the series, the answer is infinitely large, or it doesn't exist for some other reason. So let's show you another series. Suppose we start with 1, 3, 5, 7, and 9. And that's would be, what, 2n minus 1? You want to see its formula. This guy has a series, and it's 1 plus 3 plus 5 plus 7. I think just eyeballing it, would you agree that this is going to add up to infinity if you keep going? And we won't use infinity, we'll just try and remember to stick to just saying divergent when that happens. And so you might think, hey, that's not hard. If the individual terms get smaller and smaller and smaller, then the series is going to add up to something, and we'll figure out what it adds up to later. And if this thing gets just bigger and bigger and goes off to infinity, then obviously when you add it up, it's going to be infinite. And if that was true, there'd only be 2 sections, probably, maybe 3, in chapter 11. And we would have just repeated what I just said and said, hey, that's it, guys. If you want to find out what a series is, that's the rule. It's much, much more complicated than that. Much more complicated. And that's why we've got 10 other sections. If a term gets bigger and bigger as it does here, it is actually true that it's divergent. The problem is not all series whose individual terms go to 0, right? Not all of them converge to a number. Some of them add up to an infinite amount. So I'm going to show you a very particular one. It's called the harmonic series. And its sequence is 1, a half, a third, a quarter, a fifth, forever. That's what the sequence looks like. And the series is what you get if you add these up. And the series is 1 plus a half, plus a third, plus 1/4, plus 1/5, forever. And now you're just going to have to trust me on this, because I can't really prove it to you, and it's quite complicated to try and prove it to you. But this fella is divergent. And you might think, but all those numbers are getting smaller and smaller. And when you get really far along the line, you know, imagine you're at, you know, 1 trillion. It's going to be a trillionth plus a trillionth in 1 plus a trillionth in 2. I mean, those are so tiny. Surely the thing's going to add up to a fixed number eventually. And the answer is no. So here is my pseudo proof of why this is infinite. Would you agree that this sequence, this series continues forever, right? Keeps going forever. If you take these 2 terms, if you take the next 4 terms, a third, a quarter, a fifth, I guess I should put it in, a sixth, those 4 guys add up to a fraction that's a little bigger than a half. If you then take the next 8 terms, right, starting at a 7th, right, and finishing whatever it is, a 16th, the next 8 terms, they also add up to a fraction that's bigger than a half. Then the next 16 terms add up to a fraction that's bigger than a half. The next 32 terms, well, because you're playing with infinity, can't you keep doing that forever? So what does this become? Well, it becomes 1 plus a half, plus something that's a little bit bigger than a half, plus something that's a little bit bigger than a half, in fact, forever. What happens if you add up an infinite number of things that are a little bit bigger than a half? Don't you get infinity? So do you see, I don't know if that's convinced you, but do you see what I'm trying to get here is that just because the individual terms have a limit of 0 does not guarantee that when you add them all up, that the total of all those pieces isn't infinite. Right? It could diverge. So we have to figure out ways to deal with that situation. If you give me a series, how can I test whether it's going to converge to a number or whether it's going to be infinite, in which case we say it diverges.
So it goes to infinity.
Say again?
Check the limit at infinity.
Well, we could do that, but I've just tried to convince you here that in this case, the limit at infinity is 0 for this guy, whereas the series adds up to infinite. So that in itself isn't going to be an easy enough test. We have to do much more refined tests.
Well, I guess if you find out that you're dividing by infinity at some point, you'll know that you are adding up 0 numbers.
Not really, unfortunately. See, infinity plays tricks on your common sense. I can understand why you would think like, oh, these numbers are getting so tiny, they're not going to matter after a while. The problem is an infinite number of tiny, tiny things can add up to a big answer. They can actually add up to infinity in certain circumstances. That's the problem, right? These guys disappear to zero, but if you group them together, the total of them is still infinitely large. So let's show you something we're going to use a lot, and that's sigma notation. It's very cumbersome, isn't it, to write this down? Nobody really wants to have to write plus, 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 dot, 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 right? So we have a convenient way of writing down a series. This one here, for instance, I'm picking it because it's a nice easy one. Would you agree that's the formula for the sequence, right? It's much easier to write that than it is to do this. So if you want to add these up, sigma notation says, right, I don't know, did they use K or N or what did they use it? Yeah, N. So from N equals 1 to infinity of AN. You see that basically just means add up all the terms in the sequence AN. So in this one here, we would write down that. Now, isn't that a much cleaner way than writing this? And since every series is made up of adding up a sequence, don't you just need to know what the formula of the sequence is and plug it in here, and this stays put. Any questions so far, or are we good so far? Are we good? Right, let's look at adding up some terms from a sequence. Let's do that one. Do you notice that the top number is not infinity now, it's 4? So wouldn't that mean you're basically only going to add up the first 4 terms in this sequence? And since these are pretty easy numbers, it's 10 over 1 squared plus 10 over 2 squared plus 10 over 3 squared plus 10 over 4 squared. And I'm just going to do my calculator. 10 divided by 1 plus 10 divided by 4 plus 10 divided by 9 plus 10 divided by 16. And there's the horrible decimal. I don't really like it, it's kind of ugly. Let's see if I can make it a fraction then. Hit the math button, option 1, take the answer and turn it into a fraction. And the answer is 1025 over 72. As long as this expression isn't too ugly, and as long as it's not too many terms, can't you just do it by hand? If somebody, and I'm not going to do it, if somebody says 40, dot, 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 wouldn't it be nice if there was a quicker way to do it than doing them 40 times and adding them up? Right? So go and look at a video I've got, and it tells you how to do the TI-84 and use it to calculate these guys. Give you a little clue.
So on a test, if it's like this, we can just say that we used our calculator.
Oh yeah, in the number thing, I don't need to say much at all. You know how you've had a whole load of homework questions that says write down the first 6 terms of this sequence? In that question, I wouldn't be expecting to say anything except the answers, because there's no real proof or math going on there, right? Now, if it's finding the limit of a sequence, there's 2 versions. There's the ones that I just said, this is the answer, you write it down. So that would be things like the 1 plus 1 over n to the power of 2n, right? You just write e squared. But isn't there other ones where you would have to show me L'Hopital's rule or divide top and bottom by n squared, you know, or some algebra, right? So when you're being asked to find the limit of a sequence, it depends on the question, whether or not you just tell me the answer, because it's one of those questions like n factorial over n squared, the limit is infinity, right? Whether it's one of those questions, or whether it's an n squared plus 1 over 2n squared plus 1, in which case there's working. So hopefully you can say, well, hopefully you'll be able to distinguish between those two. If you don't know how to distinguish between the two, then I guess my advice would be, if you can think of working, show me it. Play safe. That's a safe way of doing it. Oh, I forgot to do something here. Let's look at a thing that's called partial sums. Imagine that you've got a sequence. So this gets a little bit cyclic. And the sequence that we've got is going to be 1 plus a half plus 1/4 plus 1/8. Obviously, I just wrote the series down there and I didn't need to. Let's do a sequence. Call it AN. And AN is going to be 1 over 2 to the n. So I'll write down what that guy looks like. So it would be a half, then it would be 1/4, be an 1/8, be a 16th, and so on. Right. So that is my sequence. If I wanted to do my series, it would be n equals 1 to infinity of AN. It would be that guy, right? Which would be essentially 1 plus a half plus an 1/8 plus 1/16, forever, right? So I guess the question that we're going to start with is there a way that we can look at this series and decide whether it's going to converge to a number and what that number is likely to be, or whether it diverges off to infinity? What's your gut feeling? Do you think this one might make it? Or do you think this one might go infinite on you? Any gut feelings?
We can put it in our calculator and we can set the number to like 1,000, and then we can set the number to 10,000. We can see if it's approaching something.
Well, depends what you're checking. And this is where some partial sums come in. Are you checking the individual terms? Because that would be easy. Don't they become 0? But we
No,
want
I'm
to
saying
check.
use the calculator to check the sum. Like we did earlier.
Perfect. That's exactly what I want you to say. Yes. We call those guys partial sums. So here is partial sums for you. They're called capital S, little 1. That's what you get when you add up the first number. It's a half. Partial sum S2 is what you get when, and I don't know where that came from, when you add up the first. That's turn it in space. The second term. And this is what you get for S3. And this is the partial sum Sn. So this is your idea, like maybe the first 1,000 terms or the first 1,000,000 terms, right? We'll just call it Sn, and n could be 1,000 or 1,000,000. If you were writing it down, I guess you would stop there, right? You know, if n was 1,000,000, you'd stop at 1 over 2 to the million. And we write that down as I equals 1 to n vi. Or in this case, sigma I equals 1 to n of 1 over 2 to the I. Now, I get a little bit, well, I'm confused at the best of times. on what variable to use here. So Sn can be I equals 1 to the n of 1 over 2 to the I. It could also be called k equals 1 to n over 1 over 2 to the k. You know these variables, the I and the k, they're just counting variables. Couldn't I use any letter of the alphabet if I felt like it? Couldn't I say well, is a bad choice. C equals 1 to n of 1 over 2 to the c? Wouldn't that be the exact same as this, which would be the exact same as that? So these are called partial sums. So let's look at the 1 over 2n one and look at its partial sums. If you add up the first term, you get a half. If you add up the first two terms, you get 3/4. If you add up the first three terms, you get 7/8. And if you add up the fourth term, you get 15/16. Numerically, does this guy look like he's getting bigger and bigger and bigger? Or does this guy look like he's beginning to level off at a number? What's your gut feeling?
It looks like it's approaching 1.
It does. If I put one more answer in, maybe I'll convince you more. Right, if you add up the first 5 terms, will you trust me, you get 31/32. So in this case here, would it be reasonable to assume that the series, we'll call it S now, the series, right? Not the L. Call it S now. It's probably got a limit of 1. So that would be an example of a series, in this case, this one here, who does add up to a number, and that number is 1. Are we comfortable with the logic that we kind of used here? We used the idea that you take a sequence that creates a series, and then that series generates essentially a sequence. It generates a sequence of partial sums. So you start with a series, you add up all the terms, and then you use that series to create a partial sum sequence. And so what you're doing is you're turning the question into, does this sequence of partial sums converge? So if the limit as n tends to infinity of the partial sums is equal to a number, in this case it's 1, we say the series converges to 1. Does the logic of how that works make sense to you? Right. So although we are dealing with series, we kind of turn them into sequences of partial sums, and we use the sequences of partial sums to decide on convergence or not. It's quite an interesting puzzle, this. The Greeks knew about it. They had a story for it. I'm going to give you a version of that story. And unfortunately, the Greeks, as clever as they were, and they were really clever, came to the wrong conclusion.
Is this the arrow and the turtle?
Not this one, but that's a version of the same problem. And this one is the frog. There was a frog. See, that's a frog. Tell him a great artist. And the distance between here and here, let's call that distance 1 foot. And this frog wants to get to the water. And it jumps half a foot on its first jump. But every jump, it gets a little bit tired, and it only jumps half as much the second time. So on its second jump, it's a quarter, and then it's an eighth, and then it's a 16th. And question that the Greeks posed is, does the frog actually reach the well? Does it get to water? Molly's shaking her head. Does the frog technically get to the water, Molly? Why are you shaking your head?
It would approach it at an
It
infinitely
approaches it.
small level.
Exactly. But the Greeks had a very bad concept of infinity. In fact, I don't think they had a concept of infinity in the way that we do. And what we are saying is not that the answer is truly one. I think, isn't it better to say it converges to one? In other words, it gets as close as you could want to one without doing it. And that just freaked the poor Greeks out, because they would argue something like, but it's always jumping. Surely it'll get to the well eventually. If you keep jumping often enough, won't you get to anywhere? Even if the steps you take are really small, if you do them long enough, won't you get anywhere, right? I mean, even if I can only walk at 1 mile a day, won't I eventually be able to walk around the world if it was continuous land? That's kind of their thought process. Do you see how infinity can play with your logic? You can have an infinite number of things and they don't necessarily do what you want you to do. So bear in mind that when we talk about a series and we say that its sum is 1 or 24 or whatever, what we're really saying is the limit of that series is approaching 1 or 24 or whatever the number is. Although very careless, and I'm as guilty as everyone, I just say it adds up to 1. But whenever I say that, well, you pretend I said the bigger sentence, its limit is 1 or something. That was pretty cool. That went reasonably well, I feel. Are we getting comfortable with the Sigma notation that we use to turn things into series? And now we're really just at the starting point of how do we tell if a series converges? Because that's pretty much the main job in most of the questions you're going to deal with.
So I like to kind of go watch YouTube videos on my free time. If I wanted to see more of that, I could look at like partial sums. Would that be a good search term?
Yeah, partial sums would be good. There's going to be a number of series you might want to look up. I'm going to start with one of them today. It's called the geometric series.
Yeah, some engineers at my work were telling me these are great.
Oh, okay. So that's the one. I've only got a few moments, but let's do an example of what's called a geometric series. Now, it comes from, not surprisingly, a geometric sequence. So let's show you a geometric sequence. You get 4, and then you get 4/10, and then you get 4/100, and then you get 4/1000. Can you see that that sequence is 4 on the top and 10 to the power of, just to be a bit awkward, n minus 1 in the bottom? Are you comfortable that that formula would generate this sequence? Okay, let's prove it. Don't you want, when n equals 1, don't you want the answer 4 to appear, right? So isn't 4 over 10 to the power of 0, 4 over 1, it works. Suppose I look at 3, right? Don't I want the third term to be this guy, right? That's 4 over 10, take away 3, take away 1, 4 over 10 squared is 100. Are you comfortable with that guy? Now, when you have a geometric series, all geometric series have 2 numbers that basically describe everything you need to know. The number A is, in this case, 4, and it's always the first term of the sequence. And the second number is the only other one you need to know, and that's R, and it's called the common ratio. Because the way geometric sequences are created is that you start with any number you like, and then whatever that number is, you multiply it by the same amount all the time. Can you see that I'm starting with 4? Because it's, you know, start any number you like. Then you multiply it by 1/10. Then you multiply this by 1/10. Then you multiply this by 1/10. So the common ratio in this case is 1/10. If you are given this formula and you want to find who A and R are equal to, right? Because they don't give you the sequence written out, but you want to know what A and R are equal to, there are 2 ways you can do it. The first way, couldn't you just find the first couple of terms and then you can just say, oh, the first one was 4, and then, yep, I'm multiplying by 10. That would work. Or you could use the fact that when you plug n equals 1, you get 4, so that's the first term. And then the common ratio, well, whatever this bottom guy is, you know, because sometimes he's going to be 3 to the n or 3 to the n plus 1 or 7 to the n. You're going to get the ratio from there. Now, in a geometric series, GS for short, if the absolute value of the common ratio is less than 1, the series converges. Now, in this case here, would you agree that the common ratio is definitely less than 1? Now, notice it's the absolute value, because you can have minus a half. So you could have an alternating sequence, right? It goes 1 minus a half plus a quarter minus an eighth plus a 16th. That would work as well. It converges. Not only does it converge, we even know what its sum is. It converges to that. Now, in this question, A is 4, and the common ratio is 1/10. So that's 4 over 9/10, which becomes 40 over 9. So this particular series, right, this one here, what you get if you add up all those terms together forever is equal to 40/9. Well, let's try and prove it to you. Isn't that 4? Isn't that 0.4? Is it not 0.04? Is it not 0.004? Can you imagine I did that for a lot of terms? Wouldn't the answer be 0.4444 forever? That makes sense? Now, what is 40/9? And I forgot, oops, I forgot my 4 at the front. So 4.4444, whatever. Are we comfortable with this works? A geometric series. If the common ratio is, the absolute value of the common ratio is less than 1, the series is guaranteed to converge. And not only that, we even have a formula that tells us where it comes from. So to finish with, I am going to prove that formula. If we start with any number you like, it's called A, great? And then you multiply it by the common ratio. So won't the next term in the sequence be A times R, AI? Won't the next one after that be AR squared, right? Because you multiply it by R. And then the next term after that would be AR cubed, forever. So isn't that the general version of every geometric series? Now, if I take this answer and I multiply it by R, it's not, yeah, by R, I get AR plus AR squared plus AR cubed plus AR is 4 forever. Would you agree? You just basically multiply all of these by another R and you up the power. Now, what is going to happen if you take this fella and you subtract that fella? So I'm going to take all of these and subtract, oops, wrong way around. take this guy and I subtract that. That's the way I went. So I take all of these guys and subtract this from it. Won't this guy get killed off by that? And this guy killed off by that, and this guy get killed off by that, and this, and technically, wouldn't they just kill each other forever? So wouldn't the only answer be left would be A? Wouldn't all the terms in the top kill off a equivalent one in the bottom if you just keep going forever? And now, if you pull out S as a common factor, and then you divide, I now know what that series will add up to. So as long as you're a geometric series, you can tell if it's going to converge. And the only thing you need to know is what's the common ratio. And if you want to find a common ratio in a series, can't you just take any two terms and divide one by the other? And that's the common ratio. And say hi and bye-bye.